The first thing we're going to do is present the the Vice Admiral Robert Goldwaith Award, and this goes out for training excellence. It's presented or sponsored rather by Boeing, and it goes to the top overall Naval Training Command Training Squadron for their performance. Now, presenting that award is going to be the commander of Trey Wing 6 right here in Pensacola. His name is Ed Heflin. Why don't you gents go ahead and take the stage. His name's Ed Heflin. Ed is the real deal. I've watched him from afar and I've watched him up close, and he is one of the most impressive Trey Wing commanders I have ever seen. I have been very free with that remark, and I would tell anybody that because he is really, truly as impressive as I'm trying to convey here. He's a Purdue grad. He has a degree in aeronautical engineering, got his wings in '93, and he was a Tomcat crew. He flew Tomcats. Now he commands Air Wing. He's going to present this award and explain why VT-22 is getting this award. So please welcome Captain Heflin.
Thank you very much, General, and good afternoon, ladies and gentlemen. I'm here on behalf of Admiral Roy Kelly, the Chief of Naval Air Training, who couldn't be here for this luncheon. He wished that he could. But the real reason I'm here is the gentleman standing behind me. As the General alluded to, this award that's so graciously sponsored by Boeing is to recognize excellence in training. And as many of you assembled here this afternoon are well aware, and I'm certain the gentlemen behind me are aware, naval aviation training is not an individual sport, it's a team sport. So while I'm going to be able to recognize Skipper Rao, Commander Rao, who's the CO of VT-22, the Golden Eagles, he has his OPSO here, Lieutenant Commander Ashton, and two recently winged aviators. You'll notice that the gold on their wings is still very shiny. They've been wearing those wings for just a couple months. And both of them are a week away from heading out to Lemoore, Naval Air Station, Lemoore, California, for follow-on training in the Fleet Replacement Squadron at VFA 122, flying F-18 Super Hornets. So these guys are really the reason I'm here today, and it's on Admiral Kelly's behalf. I'd like to congratulate Skipper Rao and his entire team, the instructors that work tirelessly to train the next generation of naval aviators, and all the support staff, reserve, active component instructors, and the contract folks who support the great work that VT-22 is doing in Corpus Christi. I will read the short citation. Vice Admiral Robert Goldwaith Award for Training Excellence is awarded to Training Squadron 22 for 2014 in recognition of superior performance in management, operations, and personnel training excellence. Signed, Rear Admiral Roy J. Kelly, Chief of Naval Air Training.
Mr. Secretary, flag officers, distinguished guests, I first need to start off by thanking the Museum Foundation and all of you for the privilege to be here. What I want to do is try to bridge the gap, if you will, between the air war in Vietnam and our part of the symposium, talk a little bit about the space, and what certainly grateful that it's the peaceful effort in space as you continue with a symposium that helps everyone focus on the history and traditions of naval aviation and the achievements that have taken us from the very beginnings of flight to flight in outer space right now, and will continue. So I didn't have the opportunity to be in the air war in Vietnam. I was on the walking side of all of that. If there are any purple foxes in the room or any scar faces in the room, you have my eternal gratitude. They were our primary support in Cobras and 46s We had A6 beacon strikes supporting us. It was monsoon season in the mountains, so we didn't see much of the blue skies or any of the VFR bombers that were out there. But all of that was my first exposure to the Marine Corps. When I got back from overseas, I decided it was time to get out of the walking business, and the Marines offered the opportunity to go into flying, to go back to MIT, to do many things that, all of which were privileges. So when people thank me for my service, I always respond that it is a privilege to serve. So it is my privilege to be here today. Now, I need to let everybody know first off that the first two letters in NASA do not stand for naval aviation. But they well could, because the history and traditions, the spirit of mission accomplishment, of exploration, and of teamwork that get the job done for naval aviation have helped NASA get the job done from the very beginning of the program. Alan Shepard, John Glenn, my personal hero as a kid growing up, all these folks, you can see somewhere in the museum here, the number of people that were involved in naval aviation in many different ways have helped us get to where we are now. In fact, from Alan Shepard to the International Space Station, we have right now flying above us an international station bigger than a football field. It wouldn't fit in this entire museum, weighs on the ground more than 1 million pounds. It was, if assembled, it was never actually assembled on the ground. So if any of you have ever had the opportunity to, the night before Christmas, put together a complicated kit and wonder how it ever was intended to go together, think about 1 million pounds of hardware built in many countries, assembled not in your living room, but in space, wearing ski gloves inside of a spacesuit. All the pieces had to fit together. It was a tremendous effort. And what's really tremendous is what we alluded to earlier. It was a team that did it. So in order to build this complicated machine, we first had to build a capable team. The NASA team was, as I mentioned, based on naval aviation and Air Force and Army and all of the engineering that came out of NACA, but we had to work with the Russians. And as we just talked about this morning, they weren't necessarily the good guys. In fact, there was some supposition that there were Russian pilots flying for the North during the discussions of the air war. I had never worked with Russians before. In fact, while flying A4s out of Yuma, Arizona, had the opportunity to go up north and sit in a MiG-21 just to see what it looked like, and to see what it looked like looking through either the gun sight or over your shoulder or any of those kinds of places. That was what stimulated me when I went back to school and I needed to study some language or study something besides engineering. I chose Russian language. So I was studying Russian language at MIT for humanities, thinking maybe I'd go back to the cockpit and back to a desert someplace and have some interesting duty. About the time I was back in school, Viktor Belenko defected with a MiG-25 and wound up in Hokkaido, Japan, I think. We gave it back to him probably in lots of small boxes, but it was at the time quite an event, and it made me think about flying other airplanes than our own in that case. Never worked out until much later. So we've got a naval aviator right there on the space station. He'll be up there for a year if everything works on that mission to help us better understand how the human body reacts to that flight. So how did we build the team, and what does that have to do with sitting around having lunch or getting to know each other or reigniting old friendships? Well, we'll talk a little bit about how that happens. First is a little bit of a geography overview. This is the view of Florida in this case from the International Space Station. So I gave away the answer to the geography quiz, and I think that for those of you who have children or grandchildren, if you were asked to know where is the center of the universe, it's right about there, just west of Orlando. If, however, you're planning to go into space, the spaceport is further to the east, and Cape Canaveral right there is where we launch and land. We don't launch right now with people, but we are moving in that direction to get there. So if we go up the East Coast and take another look at another venue, this one is important to me because of the nature of the mission that I was on. And this one is not so easy to identify, and anybody can sing out if they know what that is. But the first thing you need to know about looking at the Earth from space is that it's not always north at the top of the map or the top of the picture. And there are no signs on the ground that says this is New Jersey and that's New York and there's the Turnpike or anything else that you can click on in Google Earth. Plus, it's usually obscured by clouds. So what we did was, what's important to me about this picture is the place it was taken from. And if we pan back, now more people will recognize that that's New York City and Manhattan. In fact, we were actually looking at the United Nations right on the East River. So now we're looking at it, you can see Long Island, the Long Island Sound, and if we zoom back one more time, what you'll see is all of the East Coast almost. Up to the right, you'll see Boston, Cape Cod, and the gray area is Boston all the way to the Maine coast. You can see where New York is. Washington, D.C. is under those clouds. And further down at the limb of the Earth is where we first started with Florida and the peninsula, where we started. This picture was taken from a Soviet spacecraft. Actually, it's taken from the safe spacecraft that was put up by the Soviet Union. We took the picture because we were docked to it at the time, but it was put up as a Soviet space station in the exact same orbit that Sputnik was put up in. So if you think back to what got everybody excited about Sputnik, well, Sputnik was beeping over every city in the United States from Boston to Anchorage, Alaska, with the possibility of follow-on satellites or follow-on orbital bases or stations that had potentially hostile intent. So this is what I changed the way I was growing up and changed for a lot of us, how we looked at science and technology and engineering and the exploration of space. So when Alan Shepard, John Glenn, all those missions were going, I was watching on TV. I was a science fiction reader from the beginning. So the whole idea of flying in space made sense to me, but to actually see people doing it triggered for me and for thousands of people sort of a let's go get it attitude. So this is where we had to go. The picture that we just showed of New York City was taken from the Russian space station Mir, which was launched from Kazakhstan at the Russian base, part of the Soviet Union at the time. And if you look at it, it's made up of multiple modules. They fit together like blocks, or like Legos almost. One pressurized vessel, a can with a port at each end, connects to another one. The thing to note probably is the thing sticking out at the top is the Soyuz spacecraft. And that's what the Russians fly crews up and back in. That's what we fly with the Russians. It's still a Soyuz, slightly modified. It's the same basic vehicle that the Chinese are flying with, again, more modern engineering upgrades, but it's fundamentally that technology. The Progress vehicle is the one at the bottom of this long axis, and it's a robot. It carries cargo up, you empty it, fill it with trash, it deorbits automatically and burns up in the atmosphere, or pieces of it land in an ocean somewhere. So we've got a vehicle that can carry cargo and one that can carry crew. We're still doing that with the International Space Station, but this was, we needed to learn how to do it with them. I will mention that the Soyuz is kind of, think of an A4 Echo, only smaller in the cockpit. Yeah, with 3 guys in there. And the way you get in there is you have to crawl in through the top, and then you put your knees in your armpits. In the suit's designed to kind of crimp you into a ball so that you can move your fingers, but it's really cramped. So it is on the ground about 20,000 pounds. So that's where the comparison. The space shuttle on the ground, getting ready to go, is maybe 200 to 250,000 pounds. So 10 times more massive vehicle, and you'll see where that begins to be important when we have to dock these vehicles together. So first thing was, I had already flown twice with NASA, once as a pilot on a mission to deploy a telescope, and then as a commander on a mission to focus instruments on the Earth and help scientists understand the ozone layer and what was going on in the upper atmosphere. So I was pretty experienced when NASA selected me to go be the director of operations in Russia. I also had taken those 3.5 semesters of Russian back 10 years before and promptly forgotten since there was no MiGs in my future. But when NASA, it was actually a Marine Corps general, Jed Pearson, who said, "You're going," and he said, "Don't mess this up." Now, if you know Jed Pearson, you can pretty much get the gist of what he had in mind. The good news was that he let me define a lot of the elements of that mission so that we did develop teamwork and cooperation, because what we were about to do was exchange cosmonauts and astronauts in training bases. It wasn't a hostage exchange, but sometimes you wondered. And what we had to do was the Russians, when we got there, told us that they would help us accommodate and get acclimated and learn their equipment by never speaking English to us. So when we showed up I moved there in January, and believe me, going from January in Houston to January in Moscow is a shock in and of itself. But they said, welcome aboard, you're now in Russia, and we aren't speaking English here. So NASA had helped me a little bit remember some of the Russian I'd forgotten since MIT, but that was the first opportunity. Also, the opportunity to fly a Soyuz vehicle and work in the Mir simulator, fly a Soyuz simulator, and then I later flew with the cosmonauts in their jet planes the same way we flew them in our jets over in Houston. So first things, the launch of the shuttle, of course, we've seen a lot of it before. It is carrying, in this case, a docking module for the Russian space station, a Russian component. We get out to the pad in a van, get into the white room, and then climb into the vehicle. The only thing that's really interesting here, if you were, say, going to get ready to launch on the Alert 5 or something, you'd get into your aircraft or helicopter or whatever you were going to go out in, and climbing into the cockpit is sometimes complicated, but at least you can climb in and sit down. We climb in and then sit up. That is, you got to grab a pull-up bar and pull your feet up above your head so that it can go up into the footwells. And then there is this sort of adage that you don't ever want to be the guy who, getting into his spacecraft to launch, stepped on the main engine control panel and broke it. So you're wearing boots, you're wearing 75 pounds of survival gear, don't mess this up. So once we're in, then we're riding on what might be considered a guided missile intercept. The launch is, got a brief video, it's very dynamic, but what's kind of not recognized is we're going up to intercept a satellite which is in an orbit around the Earth, and that orbit is in a plane which is oriented, fixed to the stars. The orbit is not affected by the rotation of the Earth. In fact, as we're sitting there on the pad, or as we're here in the museum, at this latitude, with the size of the Earth, we're going 1,000 miles an hour to the east. So in that vehicle, we have to launch within 5 minutes of being exactly in the plane of the target vehicle. Otherwise, wait till tomorrow or wait till another opportunity. So it's the Alert 5 is kind of an interesting analogy here. What happens with the space shuttle, the count actually takes about 4 days. So when and that's getting everything prepped and loaded and locked and all the systems checked, in the last few seconds, the last 30 seconds, the space shuttle computers take over the launch of the vehicle itself. So there isn't a shooter, there's just the vehicle, and when it's time to go. In the last 6 seconds, the 3 main engines are ignited by the computer in order, and they go from cryogenic temperatures, they're burning liquid hydrogen, up to full throttle, and then the computer, when it sees that everything is ready to go, sends one signal which ignites the 2 solid rocket motors and explodes the 8 bolts. So if you ever think of a holdback that's going to be broken, these are pyrotechnically separated, 8 of them, 4 on each solid rocket booster. At that point, you know you're leaving. There's 7.5 million pounds of thrust pushing you. Once we clear the tower, you saw the rotation, because we're going to rotate around the long axis of the vehicle, a roll, and then start tipping out on our backs out over the water. And we actually, this is another sort of misunderstanding about rockets sometimes, we're not really trying to go up straight up. We're going up enough to get out of the atmosphere because we need to accelerate to horizontal speed. And when we do that, we know we're already we're at, let's see, 30 miles up when the 2 solid rocket motors are done. We continue to burn with the 3 main engines, and when we get to 50 miles, we actually start coming down. So now we're horizontal, accelerating at 3 Gs, and that you feel that straight through the chest, until we're at 25,000 feet per second, which is main engine cutoff speed. When we get to that point, the fuel tank, that orange thing, is empty, and we jettison the tank, Now it's still ballistically tracking with us. We move away from it, rotate it around so we can look at it and take pictures. And that's because Columbia, you may know, was destroyed on entry because during ascent, pieces of foam from the forward section of the tank separated, came off for reasons that we have a pretty good idea what caused it. But it hit the wing leading edge of the left wing and damaged the thermal protection system. So on entry, the vehicle could not withstand the heat, and the plasma, which you'll see pictures of, got inside, burned the wing off. It's an aluminum vehicle, so it's very much like anything you'd see in here as far as construction. And aluminum is not structural material at those kinds of temperatures. So good tank, and then we get in out of the orange flight suits into our everyday work clothes to do the mission that we were sent up there to do. Now in this case, we're going to attach a module to the Russian space station. It's a docking module which will allow us to, and other shuttles in the future, to join up. This is, what we're doing here is flight testing. We developed at NASA and with the crew the procedures to use the shuttle to build a space station. So now we got to go do it, and this is the first time we've tried it with the Russians in this way, and it's really the first time, it's one of those things we don't get a second chance. So I'm going to ask you to imagine you're sitting in the back of the payload bay looking straight forward at the crew module in the center of the picture. That's the left sill, the right sill of the payload bay, and you might notice we happen to be upside down relative to the Earth, and you get, after a day or two, you don't even notice. I mean, it's not important. There's no atmosphere. We're in free fall in an orbit, so we put the payload bay towards the Earth in some ways because it's easier on the payload. The Earth reflects some heat, and it keeps the payload from getting too cold. So we've used the robot arm Chris Hadfield operated the arm to position the docking module on top of the airlock and build what I called a chimney that sticks out of the payload bay. Now, I know that once I've got that attached, I can't close the payload bay doors to come home unless that thing's out of there. So there's a little bit of tension level that goes up because in order to get the mission accomplished, you got to put yourself in a position from which it's a little bit more difficult to get home if you happen to need to. So there's risks and rewards that you're trading off. So then we have about 2 more days to get closer to the space station. And now you can see why we need the docking module. The space station is not just modules. It's solar panels to gather energy, it's radiators to reject heat, it's antennas that allow it to communicate and do all the other functions, and it's made out of aluminum, and it's delicate. So remember, well, there it is. The Soyuz is visible right there at the top of the picture. There's that A4 parked at the top, and here we come with a DC-9, and we've got to collide with the space station ever so gently because the latching, the docking mechanism starts with a mechanical latch. If you don't hit it hard enough, then you would bounce off and you might be out of control or you might put the station in an unusual attitude. It gets uglier and uglier in the simulations, and most of the time, I mean, I've done that and been real sorry about it enough times in a simulator to know, I mean, that's how we train and develop procedures. So in this case, because the shuttle is so heavy and because when we maneuver, we fire thrusters, and everybody knows what thrusters do. Well, they thrust, right? Thrusters are cannons. Aimed that way, you fire it that way, and the vehicle goes this way. So if you want to go that way, fire your cannons that way. And unfortunately, if you want to stop going towards something, that means you might have to fire your cannons at it. The Russians really don't like it when you fire cannons at their spacecraft. In fact, we have to make sure that we don't, because primary rule in making a new team with the Russians, starting a partnership which is going to last for a long time, don't break the other guy's spaceship. So what we have is some very carefully calculated ways to maneuver our spacecraft. And when you fire the thruster, you've seen pictures of the New Jersey firing. I mean, it's not just the projectile that leaves the cannon barrel, it's all the hot gas, which is what we count on for thrust. Well, that pressure wave hits things like solar panels, and it could do the same thing to a solar panel that a cannon shot could do to a square-rigged sailing vessel, blow the sails off. So we are trying to avoid that by maneuvering very carefully. Our mechanical limitations are we can't collide with them with the same closing velocity as the Soyuz. We weigh too much. So our contact velocity was limited to 0.1 feet per second, plus or minus 0.03 feet per second. And we had just a couple of inches to do that in, and less than 2 degrees of misalignment because of the nature of the system. And you can't see the interface because the interface is up there at the top of the chimney where it touches the Crystal module. So we were planning to do some pretty sporty flying. Well, then the metric system stepped up, and it turned out they used the metric system. What a surprise. And our guys who think about dynamic pressures and gas pressures, we use different units, and when they think about, we think pounds per square inch, they think pascals and, well, it turns out that our cannons were a lot more powerful than they had originally thought, which meant we had to redo this. And then the Russians said, and by the way, we don't have TDRS satellites, the data relay satellites that we can use wherever we are almost on the Earth. So we want to have the docking take place overhead our ground tracking station so we can get data from our station to make sure it's all going to be okay. Did I mention that we're going 17,500 miles an hour during this rendezvous? I mean, that's the normal flight speed. So it's like precision flying. You can be going fast, watch the Blue Angels, but the relative velocity is what really counts. That's where that 0.1 feet per second. The problem is to make the contact happen, over Moscow makes the whole thing, again, we had a 5-minute launch window and we had, we were looking at 10 seconds to be, because we go 5 miles a second over the ground. So we have a relatively short line of sight window. So again, NASA teamwork and training is what allows us to get to do that. But it's also, there's an element that the Russians play in this. They aren't just passive in this whole business. So they're, once we get docked, is the commander Yuri Gidzenko of the Russian space station Mir. Now Yuri was a MiG-23 pilot, and he, back in the, call it the bad old days, he was in what used to be called East Germany with his MiG and its nose pointed to the west. You'll meet my pilot in a minute who was an Air Force F-16 driver in what used to be West Germany with his nose pointed towards the east. And we got to know these guys real well, and we went over there to visit them and train with them and eat with them and toast with them. We brought them to Houston to do the same. My wife met all these guys, and she said, you guys are all the same, not except me. Her observation as an astute observer was that pilots and aviators of whatever uniforms have very much the same kinds of mission focus, orientation, large watches, all those things, no matter what country, they're all very similar. So here we are inside the docking module, and we're presenting it officially, and there was paperwork and things from the UN, but it was a lot of fun to be there with them. Here's Yuri inside of the core module. This is the Soviet spacecraft that's been up there for 12 years on orbit. And every 3 months, a progress shows up with new stuff, and they throw away some stuff. So over 12 years, you can see that the difference between new spacecraft and 12-year-old spacecraft is kind of the way the difference is if you bought a new pickup truck, tomorrow it would look like the first one, and after 12 years, you're going to have a little more stuff in your pickup truck or your college dorm room or whatever. So we had a lot, it's a large spacecraft, a lot of complicated things going on, and we were a little worried, frankly, that although we got along well with these guys, I was the only guy on our crew that could speak any Russian. And I wasn't fluent, as somebody said. I was basic Russian. I mean, I was basic Vietnamese on the ground and a little bit more than basic Russian up there. They had one guy that could speak English, so we were trading back and forth. And to get over that and to help us with that, in fact, during the docking, where we're doing all the maneuvering, and this is that very tightly controlled circumstance so we don't hurt their spacecraft, and these guys are in it, so they're very interested in that. I switched from English to Russian so that I was given my position and status reports to Houston in Russian rather than in English, not because it was a show-off, but because they were monitoring our transmissions on UHF. So to build this team, you really have to think about, well, what's the other guy's view of you, and what's their understanding of your processes and your procedures? And it's easier for me to just speak Russian, even though it might be poorly accented or limited vocabulary, because he can tell that things are going about the way they went in the simulator on a good day in the sim. That is, it's all normal. And it made them feel a lot better rather than speak to Houston, they get a translation down there, it goes, you can see, you want to get this done face to face as close as possible and done right the first time. So taking care of the needs of your partners in this team is really important. So another difference in culture is the shuttle missions are like 10, 11 days. I mean, that's not even a cruise. The Russian missions are 6 months long. Now we've got a space station mission that's going to be a year. So they're really going on a deployment. And I've been deployed in the Marine Corps enough to know that the most important thing that the purple foxes are carrying is probably that orange mail bag. And so I want to get the mail, and when I knew we were going up there at 3 months into their 6-month mission, and we'd met their families, I made arrangements for there to be room in the shuttle cargo in the middeck in a locker to bring letters and packages and gifts from home to the Russians while they're up there. So here's Sergei Avdeyev, who is the flight engineer and an employee not of the Russian Air Force, but he works for the company that built the module. So he's the flight engineer of this thing. He's got a little bitty cabin. It's the size of a phone booth. And for those of you, well, pretty much everybody here knows what a phone booth is. When I go to a school and talk about this, you have to explain a phone. He's in there. I gave him a letter from Maria, his wife, and he's writing a return letter. That's a ballpoint pen he's got in his hand with Velcro on it. He sealed the letter in an envelope, stamped it, gave it back to me, and I carried it back on the shuttle to deliver it. So anybody that has any heartburn with the U.S. postal system being slow and old-fashioned, this is 17,500 mile an hour special delivery. And it works. I mean, it's very important to think through how we support these guys, because we help them in many different cases, and they help us as well when we need it. So Sergei got his letter and packages. Thomas Reiter is not a Russian. In fact, he was the one person that spoke English to us. He's German. So he's there with the European Space Agency, or the German Space Agency specifically, on a project with the Russians. For 6 months, they're going to study how zero-G affects the human body. Now, we're still studying that, and the problem is that we don't have enough people as subjects of these studies. So the Kelly twins are going to have a twin study and be one up and one down for a year. It's still n equals 1. That is one person. Any data you got, it's hard to expand that to a population or project future things. So we've been gathering data. In this case, these guys are up there eating a specialized diet, and then doing exercises, and then every day, and sometimes more than once a day, drawing blood, taking a urine specimen, saliva specimens. They would freeze them. TEF, if you can read that, the 2 boxes he's holding are thermoelectric freezers. They're basically fast freezers to freeze specimens, then they'd put it in a storage freezer so that later on, I mean, the data is there, it just has to be analyzed on the Earth when it's in a lab. So they told me late in the mission, we're training, that okay, here's another one of your payloads, you gotta make sure this is up there. We're carrying a freezer to bring back 90 days worth of frozen biological specimens from the 3 crew members up there. Well, remember I went to Russia in January, when the transition, that's how it worked out. One of the things, besides the freezing cold that got to me, was the fact that the Russians in Moscow seemed to ignore the cold, and they would line up at kiosks to buy. In the evening, they'd line up, the same kiosks sold beer and vodka at night, but during the day, they'd be around parks, and people would buy ice cream to eat in the park in January in Moscow. I made a mental note that these are people that really appreciate ice cream. So I'm in one of the buildings next to Mission Control at Johnson Space Center, and they say, okay, Ken, this is your payload to do this medical stuff. And it hit me instantly. I was still in the meeting, and I said, well, doctor, is this payload important? Well, when the commander of the space shuttle asked the chief investigators whether their payload is important, it's a little bit like if you're flying on an airliner and you turn in your baggage, and the guy looks at it and he says, are these bags important? Does that make you feel good about the rest of the day? But I was doing that because I'd been around NASA long enough to know which buttons to push in which order to get something done. Because NASA is a branch of the federal government. They don't have a sense of humor officially. They don't like risks that they can avoid, and they look at the crew as somewhat risky, at least the way we think sometimes. So they said, no, this is very important because this will allow us to get Soviet data and US data and join together, and we'll begin to compare databases. It's important for peace on Earth and curing hunger and everything else. So exactly what I wanted to hear. And I said, well, as an engineer, which remember, that's what NASA respects, the reliability of the freezer will be much higher. So it'll be much better chance of successful mission if we put some kind of thermal capacitance mass inside the freezer to damp out its thermal regulator, so then, it won't break during the ascent part. And so they said, they finally said, yeah, you can do that. And I said, well, the crew will find some kind of plain vanilla thermal capacitance mass to get in there, maybe chocolate chip. So I went back to the office, because I was the only crew member that, they were too busy, doing other real training stuff. And I went back and said, okay, we got to keep this quiet, because there's sort of another one of these principles that I try to follow, is that always underpromise and overdeliver. So if you tell the Russians, hey, we're going to bring popsicles or something, well, they were giving us popsicles. We're bringing ice cream. They had been all pumped up about it, thinking about it, getting there. And if something had happened, and in NASA there's always something, and we couldn't bring it, well, then their morale would have gone from way up here to way down there. It's pretty basic. Everything, I think of it as basic. I think people have been deployed. You get used to how to manage expectations. So we didn't tell them. Now, what we did do was invite the Russians officially through the State Department, NASA, State Department, Russian State Department, all the way down. Crew of Mir come to Atlantis to have a big banquet on what for NASA was Flight Day 5, Meal B, which means lunch. We get to choose whatever we want for every meal. I asked my crew, let's get all the same thing, and then we'll get 8 of everything. So we had 8 steaks, we had 8 shrimp cocktails, we had soup, vegetables, we had peach cobbler. So we brought the crew over, and this is, again, a naval tradition. You go into port with another vessel, automatically the officers leave the US flagged vessels and go to the British vessels, or go to anybody's Navy but ours, and go to the wardroom and have dinner. And that's because of Josephus Daniels. May he still be burning. So, naval tradition. So that's what we did. We brought the guys over there, and we got through down to the peach cobbler, and when Chris Hadfield broke out the ice cream, and when these guys had Bluebell ice cream with peach cobbler at the end of the meal, this just rolled their socks down. They would have given us anything on their space station at that point. We got along with those guys great, but the surprise factor and the fact that we thought about that was really stunning to them. So this was the meal that sealed the deal as far as we're concerned, and I think really did a lot to help us get along. So there we are at the end of the mission. We have the usual video conference with heads of state. We separated, leaving the docking module so that future assembly flights would be possible. Develop the team so that you can build the machine. Build the team first, then build the machine. And then we are at a distance with the docking module there is the most important part as far as we were concerned, but that was the next step. And then back into the vehicle, back into the launch and entry suits, we fired the orbital maneuvering systems engines. This is a cartoon, but the 2 engines just slow us down enough to change our orbit. Remember, we're in about circular orbit around 300 miles up, going 25,000 feet per second or 17,500 miles an hour. They're all the same. It's pretty stunning. You go once around the Earth in 90 minutes. So, but one other way to think about it is you're going Mach 25. That's fast. And you'll see what happens. Once we slow down and the vehicle gets down into the upper atmosphere, the very upper parts of the atmosphere, it's flying set up at a 40-degree angle of attack. So very nose up. This is in this depiction, the vehicle would be going straight to the right. So the whole bottom of the orbiter, the tiles, are acting not like flying surfaces. They're more like the face of a piston in a compressor. The air just doesn't know what hits it. There's no time for flow around. It's just being compressed ahead at 25 times the speed of sound. That creates tremendous heat of compression. That translates into the deceleration force that you can feel inside and a huge amount of heat. So, in fact, the shock wave out there is thousands of degrees, and it is turning the atmosphere into a plasma. In the inside, you're looking out the windows at what is kind of a view out the fireball. Now this is a view of the overhead windows, and that white wake looks a little bit like a contrail, but it's not water vapor at all. It's superheated incandescent plasma that's trailing behind the vehicle. When we turn the camera around so that you can see what it looks like on the forward windows, what you see is the inside of a fireball. It's like being inside of a meteor, perhaps, although not something you want to try. It's not hot, although in fact our suits are chilled for that just in case, and we do pre-chill the aluminum vehicle because there's a huge heat pulse that the insulation protects, but we don't want to stay in this attitude or in this condition for very long. Once we get slowed down to Mach 10, now there's an interesting concept, slow down to Mach 10. You put the speed brakes out and ease back into Mach 10. We continue down into the atmosphere. We're actually flying using the wings. I mean, the wings are load on the way up. We got to carry them along. But the wings do what wings do. Our flight path would be a ballistic trajectory that would be set at main engine cutoff. That's the direction we're going, just like a cannonball, until we get into the atmosphere and can begin to fly using the wings to get to off track. In fact, we flew 700 miles off track to get to Kennedy Space Center in what amounts to a hypersonic glider. Now, I don't know if Commander Hubbard is around, but Commander Hubbard was the CO of VT-26 in Beeville, Texas in 1972. And he liked to fly gliders at Refugio, Texas, which is just down the road a little bit. And he invited any student pilots that wanted to come to fly gliders on the weekend with the glider circle. And I raised my hand. And I am glad I did. I still fly gliders some. And this is the big one. So we glided hypersonically halfway around the Earth, but got down to line up over Kennedy Space Center. You just slow down subsonic about the time you're in the turn around the runway. Now, the HUD, which is new to NASA but not new to most people here, you get a picture painted by the HUD of where navigation thinks the runway is. And when I see that that is where the runway is, it gives me as the commander a really good feeling. What that means is that after millions of miles, nav still knows where it is, and I can then trust the guidance cues which is being provided to me. Now, we do train for night landings with no HUD, but there are a lot of people who we consider HUD cripples if they haven't ever actually flown an A4 Echo or something of that era. People get really used to HUDs. So at this point, we're looking out the left window. It's a out the window landing, looking for a very gentle touchdown. The boss of the astronaut office reminds you on just before you get onto the tower or the launch tower that this is a reusable spacecraft. So land gently. They want it all back. Now, the smoke, of course, comes because the wheels, when you deploy the landing gear in the last few seconds, they're not turning. We don't have spin up, and we don't have much tread because tread's heavy. So we've got to balance weight and performance all the way. And so we burn rubber. The runway is very rough because we want the water to drain off. It is Florida, after all, so they can get pretty well rained on. When we touch down on the main gear, we very quickly put out a drag chute for the obvious reasons. Slows us down, but it's also attached high up, which means that our landing gear, our nose gear touchdown is more gentle. The orbiter, when you see it, next time you look, I don't know if I got a picture, the nose gear is short. So when the orbiter is on its three main landing gear, or three landing gear, it's at a negative, the wing's at a negative angle of attack, and there's no tail. So when you start the derotation, there's a point at which you're coming down, and there's nothing you can do about it. So we needed to have, we timed the derotation so we can do it under control. But there's a lot of things that aviators have learned, pilots have go through, we develop procedures. We're constantly, this was different software for each flight that we were flying. So when we get back, it's very much like the return of any vehicle back to its home base or home ship. You give the vehicle back to the maintainers that own it. And that's the way we looked at it in the astronaut office. We live and work in Houston. We come down to Florida, borrow the vehicle for a week or two, and then give it back to the people that really take care of it and make sure that in about 1,000 ways, more than that, think about how many people had to do everything right, in order to make a mission successful. And that's what we think about when we're flying and then we give the vehicles back. So that very, very quickly, usually I'm speaking, and I know that the people are waiting to get to lunch after I speak. This time worked out pretty well for everybody all around. Thank you very much for the opportunity. It's been a privilege. Thank you.
Do you have time for some questions?
Sure.
Okay.
I do have time for questions, and what I'm going to have to do is move around a little bit because we're short of mics. Go ahead and tell me your question, and I'll try and repeat it.
Is there an aging factor for men and women in space?
Is there an aging factor for people in space? Probably. I think the most aging takes place while you're waiting to go, or waiting on the pad in that last few hours. You'd have to ask my wife about aging factors for people associated with the space program, because there is a fair amount of stress, and sometimes that's related to the... Well, maybe. That's one of the things people are trying to study to see how does space flight affect you. The cosmic rays aren't good for you. Whether they, it's like a lot of things that aren't good for you that you eat. You may die, but you'll never decay. So we don't know. I'm sorry, I didn't mean to be... That was not the right answer. But it's not the speed. Some people think about that you're going so fast that there might be relativistic effects. That's not happening. Any other questions?
What about over here?
Oh, yes.
Have you flown an H-46?
Yes, I have.
Then let me ask you this. Have you flown it with the SAS off, and does it make you a better astronaut?
Well, it does. It wants to fly sideways with the SAS off. Well, I mean, it's actually, I think, more happy flying straight sideways. I was at Point Mugu flying A6 Echoes, and I wanted to be a test pilot, and I'd flown A4s over, before, and so I thought, well, I'll just learn some other airplane and the aircraft. So I went over to the SAR guys who had 46s, and I said, hey, can I go fly with you guys? And the only way they'd let me fly was on post-maintenance check flights, because they had one guy, and I was, naive, so I said, sure, I'll do that. Well, most of the post-maintenance check flights involve a guy with a strobe light thing aiming it out the window at the rotor blades as they go by to make sure that they're tracking. Well, that's a really horrible ride when those aren't tracking, sitting up there in the front. But it was the only flight time I could get in 46s until later on. When I got to test pilot school, they had a 46, and they had it configured so you could fly it as all different levels of stability. So really enjoyed it. The times I was flying it in the back were less than I was part of the platoon being delivered, a little bit different. Yes, sir. Any other question? Oh, yes.
As the relationship between the U.S. and Russia deteriorates, what's happening in the cooperation between the...
It's a very good question. As the relationship between the U.S. and Russia on the ground deteriorates or gets more friction over anything from the price of oil to the Crimean Peninsula, conflict in Ukraine, name it, there's lots of sources of discontent. So far, our space program efforts have been a guidepost to better relationships between the two countries. And I attribute it to that same reason, that cosmonauts and astronauts can get along so well. Aside from, well, part of it is the farther you are from management, the better off you can do. But that's true. I mean, when we're down at the deck plate level doing things, and the commissars or bureau, farther up, life is tougher. But we cooperate because it's the worst possible environment to work safely, and that drives a certain prioritization, perhaps, of get what's most important done and let some of the other things sort themselves out. So I'm hopeful that we keep that thing going. The Russians right now have lost a Progress vehicle during ascent. During the separation from the third stage, the vehicle appears to have gone out of control or been damaged by a explosion, which then drove it out of control. And it'll most likely re-enter, people are saying May 8th or 9th. Unfortunately, the components that launch that vehicle, the Progress is the robot that carries cargo, but the launch components are the same for the Soyuz. And so until they know what really happened, you'd go through the mishap investigation, it's going to be difficult. They've delayed this next Soyuz launch for a while, and we've already lost the Orbital Sciences commercial cargo vessel. They're working on their mishap. So there's a lot of things. This is a very, very bad environment, very hazardous. So I think we'll stay on good terms with the Russians as we work through this. The next steps are whatever they're going to be, sir. Anything else? Sorry about turning my back, but thank you very much again.
That's okay. Okay, that completes the luncheon portion. The next panel starts at 1400, so you have a little bit of time to enjoy the museum, refresh yourselves, and get ready for the HAL 3 panel. Thank you very much.